Hello folks, Mr. G here, live from the nerdery, as always, doing a little bit of mathematics on a Friday night. Tonight's topic is trigonometric equations and identities. Exciting stuff. Before we begin, just a little disclaimer for you. This video alone is not enough to prepare you for the test. You need to do a lot of practice with this material on your own before you are ready to write the test. So, how should you use this video? Step 1, be sure to try each question on your own and spend a fair bit of time working on it. Don't give up too early. Once you've spent a significant amount of time working on that problem, then feel free to watch the solution in the video. If you are having a tough time with the solution, but the video helped, make sure you try the problem again on your own. And then after that, do about 20 more of the same type of problem, because practice makes perfect. Are you ready to get started? All right, here we go.
It's showtime.
Okay, here we go. Let's take a look at what we have for question number 1. Express 2 tan theta over 2 divided by 1 minus tan squared theta over 2 as a single trigonometric function and simplify as much as possible. All right. Hopefully when you see this expression in our question here, it reminds you of something we've been working with over the past few days. Specifically, something on your trigonometric identities toolbox. So let's take a look at the form of this. We have 2 tan of something divided by 1 minus tan squared of something. If we go over to our trig toolbox, let's look for something that has the same form. Searching through, nope, not quite. There it is. 2 tan of something over 1 minus tan squared of something. This is the identity we're going to use to help us with this expression. So what we need to do is we need to think of the difference between the expression that we have from our question and what we saw on the identities toolbox. So what is the difference? Well, really they're exactly the same, except for instead of x's here, we have theta over 2's. So if we want to, we could write our expression in this form. We just have to remember that instead of writing x, we're going to use theta over 2. So wherever there's an x here, there should be a theta over 2 in our expression. So this actually equals the tan of 2 times theta over 2. Okay, instead of x, theta over 2. Now the nice thing is that 2 times theta over 2 is just theta, so we can write this as the tan of theta. And that's about as simple as it's going to get. A couple lines and Bob's your uncle. Moving on to question number 2. Okay, let's take a look here. Simplify the sine of pi over 2 minus x plus the sine of pi plus x plus the sine of 3 pi over 2 plus x plus the sine of 2 pi minus x. Whoa. 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 It looks a little intimidating at first, but don't worry, there's a pretty quick way to simplify an expression like this. You might be tempted to jump into using some subtraction and addition formulas right away because you do see all the subtraction and addition happening here. And we know in the trig toolbox that we have formulas for dealing with additions and subtractions. You could do that. It would work well. Not going to be a problem. However, we're going to take a slightly different approach because of the type of angles we have. Notice that all of these here are multiples of pi over 2. Because of that, we have a nice, efficient way for simplifying an expression like this. So let's take a look. Here's what we started with originally. Now the first one, sine pi over 2 minus x, we can simplify that really quickly. Hopefully you've remembered these identities right here. We would have proven them in class, and if you'd like, I'd happily explain where they come from again. Just come and see me and I'll go over them with you. But take a look at this one. The sine of pi over 2 minus x is actually equal to the cosine of whatever angle x is. And if you look at the expression in our question, that's the first thing we have, the sine of pi over 2 minus x. So immediately, we can write that as just the cosine of x. Worked out great. This expression here, though, this is not one that I would have asked you to memorize. So how do we handle simplifying this? A quick drawing will help us out. Let's take a look at the angle here. We have pi plus x. So in standard position, pi would take us all the way around to this point, but we want a little bit more than pi. We want pi plus x. So we're going to go all the way around to pi plus a little bit more. How much more? Whatever x is. So that gives us a terminal arm in quadrant number 3. Now, I'm making a big assumption here, then that is that x is acute. Now, this actually works exactly the same if x is not acute. And if you would like to come and see me, I'll give you an explanation as to why that is. We can, in these type of questions, always assume that x is acute. The results end up being the same. If x was not acute, we'd want to consider maybe the sine graph and the cosine graph or the tan graph to help us explain why what we're about to do is true. So come see me. I'll give you a mathematical explanation as to why that happens if x is not acute, and any other mathematical explanation you want, because folks, I can give you a mathematical explanation for just about anything.
That could be a mathematical explanation for how bad your tie is.
All right, back to the question. Pi plus x. So there was our angle, pi plus x. How much did we go past pi? X, which means that x is our related acute angle. In other words, the opposite, adjacent, and hypotenuse for angle x would be the same as those for angle pi plus x. The only difference is the signs of the opposite and the adjacent might be different. So we can write sine of pi plus x as the sine of x. There's only one thing we have to watch out for. We are in a quadrant where only tan is positive. So the sine ratio would work out to a negative. And that's mainly because, well, it is because the opposite side here, if we drew the triangle, would be a negative value. So here it is. We can rewrite this expression as the sine of x. We just got to remember to make it negative because it's in the tan quadrant. For the remaining two pieces of our expression, we're going to take a similar approach. So 3 pi over 2 plus x. Let's draw that. 3 pi over 2 would take us all the way around here, but we want a little bit more. How much more? Whatever x is. So that little bit there that we go past 3 pi over 2 is x. Okay, 3 pi over 2 plus x, which means this here is x. Now that's not the related acute angle though. It's in the wrong position for the related acute angle. The related acute angle is always between the terminal arm and the x-axis. So the question becomes, well, what is the related acute angle? You can get that by thinking about what this angle is here. The angle between these axes here is 90 degrees, or in radians, it's pi over 2. So if this angle is x, this angle must be whatever 90 degrees take away x is. Now we are working in radians, so instead of 90 degrees, we'll say pi over 2 minus x. All right, so the whole angle is pi over 2. That's x. So this must be whatever you get when you take x away from pi over 2. So your related acute angle is pi over 2 minus x. In other words, we can write sine of 3 pi over 2 plus x as the sine of the related acute angle. But because we're in the cosine quadrant, sine should be negative. So we'll go subtract the sine of the related acute angle. Last but not least, 2 pi minus x. Well, 2 pi would be a full rotation. We don't quite want that though because we're subtracting whatever x is. So 2 pi minus x might look like a full 2 pi just backed up a little bit. We didn't quite make it around. How much did we back up? Whatever x is. So the whole angle is 2 pi minus x. The related acute angle in this case is x because that's how much we subtracted off from 2 pi. So we can write sine of 2 pi minus x as sine of x. Again, though, we are in the cosine quadrant. Sine would be negative, so we just need to remember to write minus sine x. Okay, looking at this here, it's definitely getting better. We just have to deal with this here. Now, you might think, well, it's not really any better than it was in the previous line, 3 pi over 2 plus x, but I disagree with you because sine of pi over 2 minus x, as we saw earlier, can be written as cosine of x. So in the next line, we'll rewrite cos x. We'll rewrite minus sine x, but this here we know is cos x, so we can just write minus cos x and then minus sine x. We have a cos x minus a cos x, so we can subtract those off. They are gone. And negative sine x minus sine x can be written as negative 2 sine x. And there it is, simplified all to negative 2 sine x. Let's move on to question number 3. Determine the exact value of the trigonometric ratio sine 5 pi over 12. And then make sure you rationalize the denominator. Okay. There are a couple ways to go about handling this question. You can actually do it with the double angle formula. The reason you would know that the double angle formula would help you out here is because if you double 5 pi over 12, you get 5 pi over 6. The related acute angle for 5 pi over 6 is pi over 6. And we know that pi over 6 appears in our special triangles, so it's going to be something nice to work with. I'm not going to take that approach right now. We will see some double angle formula a little bit later on in this video. For now, I'm going to use an addition formula. The way that we're going to do it is rewrite 5 pi over 12 as 3 pi over 12 plus 2 pi over 12. You might think, well, why did he choose 3 and 2? Why didn't he choose 1 pi over 12 and 4 pi over 12? The reason I chose 3 and 2 is because of what these fractions will reduce to. 3 pi over 12 will reduce to pi over 4. 2 pi over 12 will reduce to pi over 6. Now, these angles, pi over 4 and pi over 6, these are angles that we like to deal with because they are in the special triangles and we can easily get exact values for the trig ratios of these things. And it's from here that we're going to use our addition formula. So we have the sine of something plus something. Our trig toolbox says that the sine of x plus y can be written in this form. And this is what we're going to do. We're going to write it out in this form in our question, but instead of x and y, we are going to use pi over 4 and pi over 6. So here it is. The sine of pi over 4 plus pi over 6 is the sine of pi over 4 cos pi over 6 plus cos pi over 4 sine pi over 6. Now all we have to do is use our special triangles to help us evaluate these. Okay, so looking at our special triangles here, the sine of pi over 4, there's pi over 4. Sine is opposite over hypotenuse. We can write it as 1 over root 2. And we'll do the same for the other angles and ratios. And it does turn out to be 1 over root 2, root 3 over 2, plus 1 over root 2, and 1 over 2. Okay, just rewriting these using the special triangles. All right, a little bit of multiplication. 1 times root 3, root 2 times 2. Similarly here, gives us this. Oh, look at that. We've already got a common denominator, so we can combine, add them together, which would be fine if the question didn't ask us to rationalize the denominator. Notice we have a root here, and we don't like that in math. So we can get rid of the root 2. And all we need to do to get rid of the root 2 in the denominator is multiply the denominator, and therefore also the numerator, by root 2. Root 2 times root 2 here will give us 2 times 2 gives us 4. And in the numerator, when we multiply up there, we just have to remember to distribute. So root 3 times root 2, which is root 6, and 1 times root 2, which is root 2. And there it is, the final expression, the exact value of sine 5 pi over 12. Sound good?
I'm just checking your math on that. Yes. I got the same thing.
Good. All right, moving on. Question number 4. Question number 4. If tan x is negative 3/4 and x lies between 3 pi over 2 and 2 pi, determine the exact value of sine 4x. All right, how do you know where to start in a problem like this? The first issue that I notice is that we're dealing with two different arguments. Here, we have tan of just x, but we're being asked about the sine of 4x. So x and 4x. If we're going to succeed here, we need to somehow relate 4x to x. There's a couple ways you could go about doing this. You could say that 4x is 2x plus 2x, and then you can use an addition formula there and break it down further using more addition formulas or double angle formulas. But I'm going to take an approach here that uses a double angle formula right off the top. So what we're going to do is express sine 4x as the sine of 2 times something. Hence the double angle, 2 times something. Sine 4x, well, 4x can be written as 2 times 2x. Okay, so now we have sine written, we have our expression written as 2 times something. So we're ready to use a double angle formula. Now, if we look at the double angle formula for sine, we see that the sine of 2 times something is equal to 2 sine x cos x. So in other words, when we were doubling x, we have an x here and an x here. Now in our question, we're not doubling x, we're doubling 2x. Take a look here. So you're doubling 2x. So instead of writing out x and x here, we're going to write 2x and 2x. Here it goes. All right, so just using the sine double angle formula, we've got 2 sine of 2x, cos of 2x. Now we're getting closer. Our whole goal is to start talking about sine and cos and tan in terms of just x. Currently, we're using 2x, but we can once again use the double angle formulas to rewrite these in terms of x. Now, sine 2x, pretty much I'm just going to write down the actual double angle formula's right side here. Sine 2x is 2 sine x cos x. So we can write that one down. Now, as for the cos of 2x, you've got some choice. We can use this one, or this one. And to be honest with you, in this question, it makes no difference. It's going to be about the same amount of work in the end. So I'm just going to randomly pick one. And that one is going to be, we'll see in a minute here. Okay, there's 2 sine of 2x. We just wrote using the double angle formula as this. And the cos of 2x, here it comes. Oh, we chose 2 cos squared x minus 1. Okay, you could have gone with one of the other two if you like to. It makes no difference in the end. All right, so where do we go from there? Well, the good news is everything's in terms of just x now. There are no more 2x's, and there are certainly no more 4x's. All we know about x, though, is that its tan ratio is negative 3/4, and it lies between here and here. So how are we supposed to figure out the sine and the cosine ratios so that we can actually evaluate this? Well, if we draw it, we know that x, the angle x, lies between, lies between, yes, 3 pi over 2 and 2 pi, which is going to put you in quadrant number 4. Tan is negative 3/4. In other words, opposite over adjacent should be 3 over 4. So we can write our opposite in as 3 and our adjacent in as 4. Now, some people like to write negative 3 here because we have a negative value. I'm not going to do that, but if you want to, feel free. There's lots of different ways to go about writing this and handling it in general. Now, if we have a right angle triangle here, 2 legs, 3 and 4, the hypotenuse is 5. Hopefully you remember that this is the famous 3, 4, 5 triangle. You could also use the Pythagorean theorem to figure out that the hypotenuse is 5. Okay, so we've got it ready to go. What's the sine of x? Well, sine is opposite over hypotenuse. Our opposite is 3. Our hypotenuse is 5. So you might say, well, sine of x is 3 over 5. True, but watch out. We are in the cosine quadrant here, so we have to remember that sine would be negative. And once again, that's because the opposite is negative. So we can write sine x as negative 3/5. We're also going to need to know the value of cos x, though. Cos is adjacent over hypotenuse. Our adjacent is 4, and our hypotenuse is 5. And we're in the cos quadrant, so it's going to be positive. We can write the cos of x is simply 4 over 5. These values will now be substituted in this expression. All right, ooh, look at that, fancy graphics. Okay, 2 sine x we know is this, cos x is 4/5. 2 cos squared x just means take the value of cos x and square it, and minus 1. Grab your calculator, or better yet, do some mental math. We get this and multiply for a final answer of negative 336 over 625. That is the exact value of sine 4x. All right, let's move on to question number 5. All right, question number 5 is dealing with solving trigonometric equations, and it looks like we have 4 of them to solve. We are going to handle each of the 4 pretty much in the same way with just a couple of subtle differences. So starting with part A, negative 5 cos x plus 3 equals 2. All right, first thing to notice is we are working with a restricted domain. We are only interested in x values that lie between 0 and 2 pi. So if you get any answers outside of that domain, you can ignore them or discard them. We don't need them. Okay, so moving on here. Negative 5 cos x plus 3. Well, the whole goal in solving a trig equation is to find the value of x. So let's start to isolate x. For example, we can subtract off 3 from both sides. 2 minus 3 is negative 1. We could also get rid of this negative 5 by dividing by negative 5. Negative 1 divided by negative 5 is 1/5. So now we know that cos x is 1/5. So where do we go from there? Well, we need to find what x is, and x is an angle. Unfortunately, we don't have a special triangle with side lengths of 1 and 5, so we can't take that approach. We can, however, use our calculator. We can actually inverse cos 1/5, and our calculator will tell us the angle. Now, you might be wondering, should I be in degree mode or radian mode? Whenever you're in doubt there, just take a look up at your domain. You'll notice that the domain is given in radians, 0 to 2 pi, so make sure your calculator is in radian mode. Okay, so with your calculator, inverse cosine of 1/5, that's going to give you the smallest angle x such that the cos of x is 1/5. In other words, we are finding our related acute angle. Okay, inverse cos of 1/5 works out to about 1.369. That's your related acute angle. From there, we notice that we are dealing with a cosine that works out to a positive value. Okay, 1/5 is positive. That tells us what quadrants we must be dealing with, and cosine is positive in quadrant 1 and quadrant 4. So we draw it. Quadrant 1, terminal arm, related acute angle is 1.369. So the angle in standard position measured from the positive x-axis counterclockwise, we get an angle x that is actually 1.369. We are asked to round in the nearest hundredth of a radian though, so we can round that to 1.37. That's our quadrant 1 option. Let's take a look at our quadrant 4 option. Terminal arm in quadrant 4, the related acute angle is 1.369. We need to find the angle in standard position. How do we do it? Well, we take a full 2 pi, which would be all the way around, subtract off 1.369, and that'll give us our angle x. Okay, so 2 pi minus 1.369 on your calculator, rounded to the nearest hundredth, works out to about 4.91. Notice both of these numbers do fall within our domain. 0 to 2 pi. 2 pi is about 6.28. It's 3.14 times 2. And both of these numbers fall between 0 and 6.28, so we are good to go. Just a final therefore statement to sum things up. X is approximately 1.37 or 4.91 radians. You are done. Let's move on to part B. Okay, part B, it's the same question, same domain, but a different equation. 2 sine 3x, ooh, yikes, 3x. 2 sine 3x plus root 3 equals 0. Okay, the big problem here is this 3x. This is going to cause us some issues, but we'll take it one step at a time and see what happens. As usual, we're solving an equation, so the goal should be, let's isolate x. We can subtract off a root 3. There it is, negative root 3 on the right side. We can divide this 2 out, giving us this. You might want to try to divide by 3 here, but dividing this by 3 is not going to get rid of this 3. Don't forget, this 3x is being signed. So if you want to get rid of the 3 by dividing, you'd have to first get rid of this sign, get it out of the way. So we need to take a different approach. The way we're going to do it is we're going to do exactly what we did in question A, except instead of solving for x, we're going to start by solving for 3x. So for the sake of what we're doing, we might as well just imagine that this is just x. Okay, so here we go. For 3x, let's find the related acute angle. Lucky for us, root 3 over 2, those are so root 3 and 2 are side lengths in a special triangle. Let me just bring that up for you here. Root 3 is there and 2 is there, and we're taking the sine. So opposite over hypotenuse would mean that we had to have been using an angle of pi over 3. So our related acute angle is pi over 3 from the special triangles. We also know that we're dealing with a sine ratio that works out to something negative. Okay, looking right there, it's negative, and that tells us what quadrants we're working with. Where sine is negative, that would be quadrant 3 and quadrant 4. Okay, so we draw some pictures. Quadrant 3, terminal arm, related acute angles pi over 3. We need to find the angle in standard position measured from the positive x-axis counterclockwise. We can get that by taking pi and adding pi over 3. So pi is 3 pi over 3 plus 1 pi over 3 is going to give us 4 pi over 3. And that's one of our values. But keep in mind, that is a value for 3x. Okay? Pi plus pi over 3 is 4 pi over 3. That's one of our values for 3x, not x. Now, there's something going on with this comma here. That must mean there's more answers. What's going on with that? Well, here's the deal. X had to lie between 0 and 2 pi. But remember, right now we're not dealing with x. We're dealing with 3x. So if x had to fall between 0 and 2 pi, 3x must fall between 3 of these and 3 of these. In other words, 0 and 6 pi. So that's right, we can actually go up to 6 pi if we're talking about 3x. What does that mean in terms of our answers over here? Well, if we were to add a full rotation to this, we'd end up in the same spot. That'll give us another answer, and as long as it's not over 6 pi, we can use it. Now, a full rotation is 2 pi. So if we're currently at 4 pi over 3, and we add another 2 pi, what do we get? Well, 2 pi can be written as 6 pi over 3. So if we take 4 pi over 3, and we add 6 pi over 3, we get 10 pi over 3. Okay? And we can actually add another 2 pi, which would be another 6 pi over 3, giving us 16 pi over 3. Now, can we go one more? No. We're only allowed to go up to 6 pi. And over 3, well, 6 pi would be 18 pi over 3. We can't go past 18 pi over 3. If we tried to add another 2 pi, we'd go over 18 pi over 3. In other words, we'd go over 6 pi. No can do. All right, so that was our quadrant 3 option. Let's take a look at our quadrant 4 option. Terminal arm, quadrant 4, related acute angle, as we saw here, is pi over 3. We need the angle in standard position. We can get it by taking a full 2 pi and subtracting pi over 3. 2 pi is 6 pi over 3. Minus 1 pi is 5 pi over 3. So this angle is 5 pi over 3. Keep in mind, this is 3x, not x. Okay. Again, we are allowed to go up to 6 pi. So we can start adding 2 pi to this and get more answers as long as we don't go past 6 pi. So I'm going to take my 5 pi over 3. I'm going to add 2 pi. In other words, 6 pi over 3 gives us 11 pi over 3. If I add another 2 pi, that is another 6 pi over 3, it brings me to 17 pi over 3. We are right next door to the angle being too large. We're only allowed to go up to 6 pi, which is 18 pi over 3. We're at 17 pi over 3. We can't go any further. We can't add another 2 pi. So there's 6 answers for 3x. How do we get the answers for x, the values of x? We just need to divide all these by 3. Okay, and 4 pi over 3 divided by 3 would be 4 pi over 9. Divide by 3 here, we get 10 pi over 9. No surprises here, folks. They're all just over 9 now. No big deal. 6 possible answers here for x. Just to be polite, once again, final therefore statement and write them in order. Okay, it's just being courteous. And there they are. Lots of answers for this one. It's a big one. Okay, let's move on to question C. Same question, different equation. Right away, this looks a little intimidating because of all the trig ratios that we see. We've got a sine x plus another sine x times a tan x. So where do we even begin? You might want to try turning this tan into a sine over cos. But before you go and make a big change like that, it's always a good idea to see, can you factor? All right, we know that factoring's played a huge role in solving equations up to now, so let's try to use it here. Each term does have a sine x in it. There's a sine x here, and there's a factor of sine x in this term as well. So what that means for us is we can actually common factor out a sine x. Now when we do that, we get sine x times 1 plus tan x, and you can check it. Sine x times 1 is sine x, and sine x times tan x is sine x tan x, so we did factor correctly. You might remember this thing that you've been dealing with for years now called the zero product property. And what the zero product property states is that if you have something times something equal to 0, one of these two somethings has to equal 0. In other words, maybe we have sine x equals 0, or maybe we have the 1 plus tan x factor working out to 0. At least one of these has to happen if this thing's going to work out to 0. Now, to find out where sine x equals 0, you don't need to use related acute angles and all that stuff. Just go to the sine graph, okay? Whenever you have sine x equals 0, 1, or negative 1, check out your sine graph. It's really easy to see on a sine graph where the value of zeros occur. We know that sine starts at 0, and then it goes up and comes back down and hits 0 again at pi, and then it goes down and comes back up and hits 0 at 2 pi. And you can take a quick look at the sine graph to see this. It hits 0 at 0, pi, and 2 pi. Now, it hits 0 at a lot of other values too, but we only have to deal with the ones from 0 to 2 pi. All right. 1 plus tan x equals 0 means that tan x has to equal negative 1. So you could at this point grab your calculator, do the inverse tan of 1 and find the related acute angle and so on, but you can actually use the special triangle here. If we look at this special triangle, we want to get the ratio to work out to 1. If we use an angle of pi over 4, tan would be opposite over adjacent, so that's 1 over 1, which is 1. We don't need to worry about the negative right now, that's just going to tell us the quadrants. So if tan x equals 1, we must be using an angle of pi over 4. 1 over 1 is 1. So the special triangles tell us that, in this case, the related acute angle actually is pi over 4. We do have to pay attention to the negative, though. Okay, tan is a negative value here, which means we're working in quadrants where tan is negative, and that is quadrants 2 and 4. So we go and draw a picture. Quadrant 2, there's your terminal arm. We know the related acute angle is pi over 4, but we need to find the angle in standard position. We can do that by taking a full pi and subtracting pi over 4. That is a full pi, which is 4 pi over 4, minus 1 pi over 4. We get one possible value for x is 3 pi over 4. Moving over to quadrant 4, terminal arm quadrant 4, related acute angle is pi over 4. We need to find the angle in standard position. How are we going to do that this time? Well, if we went all the way around, that would be 2 pi, but we want to subtract off pi over 4 to get us to here. So 2 pi, which is 8 pi over 4, minus 1 pi over 4 is 7 pi over 4. And there are your two possible answers. Oh, my mistake. I completely forgot that we have these ones too. Okay, so we have 5 answers altogether. Don't forget to do that on the test. If you've got these 2 here and these 3 here, we have a total of 5 answers. We write them all in order, and there are your 5 possible answers for solving this equation. All right, let's move on to part D. Same domain, same type of question, except holy cow, things are getting pretty serious now. We not only have cos squared x, but we also have cos of 2x. No! Now, don't be too concerned about the cos squared x. That just means that we're probably dealing with something here that's going to be a non-linear trig equation. It is a non-linear trig equation. The big problem is that we have different arguments. We have some cosines where the argument is just x, but we also have a cosine where the argument is 2x. This here is problematic. We need to take care of that immediately. The way we're going to do it is using a double angle formula. If we look at our trig toolbox, there we go, cos 2x, there's 3 different ways we can write this. Now, if we look back at our expression here, there's no signs anywhere else in the equation. So it wouldn't make sense really to go with one of the the cos 2x expressions that involve sine. We're going to go with this one right here. There's no sine on this, so it's 2 cos squared x minus 1. We'll just go back and replace cos 2x with 2 cos squared x minus 1. Everything else is exactly the same as it was in the previous line. Now it looks pretty big, a little intimidating perhaps, but the good news is the only argument in this now is x. All right, we have a quadratic trig equation with just x as the argument. So let's rearrange it here. We'll put everything on the left-hand side. So we'll add 4 cos squared x to each side, subtract off 5 cos x. Anyway, it ends up looking like this. Okay, 6 cos came from 2 plus 4, negative 5, and negative 1 minus 3 is negative 4. So where do we go from here? Well, it's a quadratic type of equation. It's got trig stuff in it, but it's still quadratic. So we can think back to how we used to solve quadratic equations when there were no trig expressions in it. In other words, imagine this as being something that looks like this. Okay, instead of the coses, we can think it's just 6k squared minus 5k minus 4, right? 6 times something squared minus 5 times something minus 4. How would you have solved this in the past? Hopefully, it would factor. Okay, if it doesn't factor, we can still solve it using the quadratic formula, but this one actually does factor into this. So we can factor this. The only difference is, instead of k's, we'll be using cos x's. Check this out. All right, see the comparison, see the similarities here? 2 cos x plus 1, 3 cos x minus 4. Going back to that zero product property idea, if this is going to equal 0, one of these two factors has to work out to 0. So maybe 2 cos x plus 1 works out to 0, or maybe 3 cos x minus 4 works out to 0. Let's start with this one. A little bit of rearranging. Subtract 1, divide by 2. Cos x has to equal negative 1/2. 1 and 2 are sides from the special triangle, people. So looking at the special triangle, if the cos is going to work out to 1 over 2, that means the adjacent has to be 1 and the hypotenuse has to be 2. The angle we're dealing with has to be pi over 3 then. So that's your related acute angle is pi over 3. We know that cos is negative, tells you that you have to be working in quadrants where cos is negative, that is quadrant 2 and quadrant 3. Draw a picture in quadrant 2. Related acute angle we know is pi over 3. We just have to find the angle in standard position. So we can take pi minus pi over 3, which gives us 2 pi over 3. Okay. We also have the quadrant 3 option. There's the arm. Related acute angle is pi over 3. So we got to find our angle in standard position. We can take pi plus pi over 3. So 3 pi over 3 plus pi over 3 will give us 4 pi over 3. So 2 possible answers here. Moving on to the other option, which is 3 cos x minus 4 equals 0. If we rearrange that, we get cos x equals 4 over 3. Now you could try to do the inverse cosine of that on your calculator, but it's going to give you an error. You might have realized right away that this is actually impossible. The reason is because 4 over 3 is larger than 1. It's 1.333333333 and so on. But you also know, like, the cos graph doesn't go higher than 1. So if the cos graph doesn't go higher than 1, how are we supposed to get cos x working out to 4/3? You can't do it. And that tells you that this little equation here has no solution.
It's a problem with no solution.
So we only have our two answers back here. X equals 2 pi over 3 and x equals 4 pi over 3, and that's it. Two answers for this one. All right, let's move on to question number 6. Question number 6 is where we are asked to prove some trigonometric identities. This is usually a great source of fear for students. A couple ideas though. First thing is this, make sure you get something written down, because even if you don't complete the full proof, you can still get some part marks for some correct ideas and some correct work. The other thing that I'm going to stress as we work through these proofs is always try to plan ahead. Okay, if you look where you're going, you can usually get some ideas of where to go in your next step. All right, so let's start with part A. This is the identity that we're asked to prove, so we always start by splitting it up into the left-hand side and the right-hand side. So we got our left side, which is sine 2x plus sine x over 1 plus cos x plus cos 2x. And we have our right side, which is the cotangent of pi over 2 minus x. Okay, so before you dive into making a bunch of substitutions, let's just talk about this for a sec. We have some problems that we need to deal with, the biggest of which is there are different arguments everywhere. We have some arguments that are x, we have some that are 2x, and we have some that are pi over 2 minus x. This is an issue that we need to deal with right away. So where do we go? Well, instead of just taking care of everything immediately and getting rid of everything, look at the options where you really don't have any choices. For example, sine 2x, if we look at our trig toolbox, for sine 2x, we only have one option. So it makes sense right now to change sine 2x into its equivalent expression of 2 sine x cos x. Notice I didn't touch the cos 2x. The reason is because on the trig toolbox, we've got 3 options for that, and I don't know which one I want to use yet. Now, if we look over here, though, we can start working away at this too, because this is an argument that's not just x, it's pi over 2 minus x. So we can deal with that. Now, some of you know, just from experience at this point, that this is equal to tan x. Okay, and I'd be happy to give you an explanation on why that is. Actually, we'll see through this proof why that is. But if you didn't know that this is equal to tan x, don't worry about it. We can figure it out right now. If you do know that it's tan x, you can actually just write equals tan x if you want. Cotangent of x, or anything really here, cotangent of x in this case is cos x over sine x. Okay, so we can write cotangent of pi over 2 minus x as cos of this over sine of this. And that's what we're going to do right now. So what was the point of splitting that up like that? So that we could use these other 2 properties that we've seen before. Notice that you've got cos of pi over 2 minus x and sine of pi over 2 minus x. It's this pi over 2 minus x thing that you need to recognize and realize that from what we saw in class, sine of pi over 2 minus x is cos x, and cos of pi over 2 minus x is sine x. So we're going to change those. We're going to change this into sine x, and we're going to change this into cos x. That looks much better. And we're going to stop there. Oh, by the way, sine over cos is tan, so that's how you know that this up here is actually equal to tan. But we're going to leave it at that, and now our whole goal becomes trying to get the left side to say sine x over cos x. How are we going to do it? Well, again, we need to make a really good choice on what to choose for cos 2x. Okay, I'm not saying you couldn't choose. I'm not saying that there's wrong ones to choose. It's just that choosing the right one will get you to the answer much more efficiently. Okay, so what could we do? Take a look upstairs. Anything we can do up there? Well, we do have a factor of sine x here and a factor of sine x here. And if we look where we're going, we need a sine x up top. So what I'm going to do is I'm going to factor out a sine x in the numerator. Leave the denominator untouched. I know that I want to leave this sine x here because of where I have to end up. Okay, so the goal for me now is to get rid of 2 cos x plus 1. That is going to help me choose a substitution for cos 2x. Okay, if you look where we're going, we should have a cos x in the denominator. Okay, now currently we have a bunch of cosines here. We've got to get rid of the cos 2x. Which one should we choose for our double angle formula from our trigonometric toolbox? Well, we have 3 of them. 2 of them have sine. 1 of them has only cos. I'm going to go with this one here, 2 cos squared x minus 1. I'll do the substitution now, and I'll just explain for a minute why this makes sense. If you look on the bottom here, we've made the substitution. Cos 2x is 2 cos squared x minus 1. I want to try to do something with this denominator that allows me to cancel with this and leave me with just a cosine of x. Notice it's all coses. If I want it to cancel with this only has coses in it. And if I want to be left with this, it's another expression that only has coses. It wouldn't help me much to have any signs down here. I don't want anything to cancel with this sign because I need a sign in the end. That's why I chose this representation of cos 2x. So from there, we can simplify. Notice we have a 1 minus a 1, so that's gone. And in the bottom now, we have cos x, and we have another term that has a factor of cos x. So we'll just move up here. Factor out the cos x on the bottom, leaves us with this. Now here's the good news. 2 cos x plus 1 and 1 plus 2 cos x. These are the exact same expression, just in a different order. So we can actually go and divide those, and there it is. It works out to sine x over cos x, which is the same as the right-hand side. So we just write our therefore statements. The left side does equal the right side. Therefore, our identity is proven. Okay, so always be looking ahead. Look where you're going and let that guide the decisions that you make. Okay, let's move on to part B. Question B, we have another identity here, and we'll start it off the exact same way by splitting it up into left side and right side columns. On our left side, we have secant x minus cos x times cosecant x minus sine x. And on the right side, we have tan x over 1 plus tan squared x.
I can work it out. All I need is time.
All right, so pencil goes down. We need to look at this for a minute and kind of decide where to start. The first issue that we see is that there are secants, cosines, cosecants, sines, and tans involved. Okay, lots of different types of trig ratios going on here. Usually when that happens, what you'll want to do is get everything in terms of sines and cosines. So that's what we're going to do here. We're going to start with the left-hand side. Secant x can be written as 1 over cos x. Cosecant x can be written as 1 over sine x. Okay. Now we could go over to the right-hand side and start changing that into sines and coses. But let's see if we can tidy this up a little bit. I mean, it's starting to look messy. We know that this side's a single fraction. Perhaps by expanding this, we can make it look a little bit better and easier to work with. We can do that, but we need to remember to distribute. So we'll get 1 over cos x times 1 over sine x, which is 1 over cos x sine x. We'll get 1 over cos x times negative sine x, which is negative sine x over cos x. Negative cos x times 1 over sine x is cos x over sine x. And negative cos x times negative sine x is positive cos x sine x. We can simplify this more, but in order to do that, we need to get a common denominator so we can subtract and add these expressions. So a quick glance at our current denominators tell us that an ideal common denominator would be cos x sine x, because it's easy to change our other denominators into cos x sine x. Okay, so here's what it's going to look like. Let me just explain this. The 1 is already over cos x sine x, so there's your 1 right there. In order to get cos x sine x for this denominator, we need to multiply it by sine x. So we multiply the top by sine x as well, giving us minus sine squared x. This denominator needs to be multiplied by cos x to get this denominator. So we have to multiply the top by cos x, giving us minus cos squared x. Last but not least, cos x sine x here currently has a denominator of 1, so it needs to be multiplied by cos x and sine x to get the common denominator, which means the top needs to be multiplied by cos x and sine x, giving us cos squared x and sine squared x. All right, so pencil goes down again. We got to think, okay, what can we do here to make it look a little bit better? All right, you might think, I don't want to do anything right now. I want to go and work on this side. Hey, that's fine. Go ahead. But as soon as you see all these sine squareds and cos squareds, think of these Pythagorean identities, in particular the first one here, sine squared x plus cos squared is 1. You can probably use that to simplify it. Now again, plan ahead a little bit. Don't be random. Don't just go and change sine squared into 1 minus cos squared and change cos squared into 1 minus sine squared. It'll work and it's not wrong, but you might be doing a lot more work than you need to. Remember, our goal here is at this point to make this look a little bit better. If you notice you have a 1 minus sine squared x, you can change that right away to cos squared x, which will, as you can see, work out really nicely because we're going to subtract cos squared x. So you know that sine squared plus cos squared is 1. So 1 minus the sine squared would give us cos squared. It's just rearranging the Pythagorean identity. So we're going to change this 1 minus sine squared into cos squared. The nice thing there is, look what you get. Cos squared minus cos squared. That's 0. We don't have to write it anymore. We're left with cos squared sine squared over cos sine of x. Okay? And we can actually divide here. Cos squared divided by cos x, sine squared divided by sine x. We can do a little bit of simplification, leaving us with just cos x sine x. We are not going to get any simpler than that. So now we know it's definitely time to start working on the right-hand side. So we venture over to the right-hand side. Everything is currently in tans. Look where we're going. Plan ahead. Cos x sine x, we need to get these in terms of cos and sine. From our trig toolbox, we know that tan is equal to sine of x over cos of x. So we can change those into sines and coses. Now be careful here. Tan x is sine x over cos x. Okay. We still have 1. Tan squared x means tan x all squared. So it means sine x over cos x all squared. And exponent rules say we can just square the sine and we can square the cos. Okay, so tan squared is sine squared over cos squared. It looks a little bit messy. Ideally, we want to bring it down to this. How are we going to do it? Well, we do have a fraction divided by something that involves fractions. So you might be thinking I need to multiply by the reciprocal, but it's not ready for that yet. In order to do that, you need a single fraction on the bottom. We currently have 1 plus a fraction. But a common denominator will get us there. We have a cos squared x as a denominator here. It's easy enough to get 1 to be a fraction with cos squared x as its denominator. We'll just write it as cos squared over cos squared. And then we can add them together, and we'll get cos squared plus sine squared all over cos squared. And there it is right there. This hopefully jumps out to you. Cos squared plus sine x squared. Oh yeah, that's 1. So right away, without hesitation, change it to a 1. We now have a single fraction divided by a single fraction, so we can flip the fraction in the denominator and multiply, standard fraction arithmetic. You get sine x times cos squared x over cos x times 1. We get some great things happening here because we can divide cos x nicely into the numerator, giving us just a single cos x on top and no coses in the bottom. And there it is. Sine x cos x. Now, if you're being really picky, we can change the order to cos x sine x so it looks exactly like the left-hand side. Not really necessary, but why not? We are done. Left side does equal right side, so state it. You have successfully proven the identity, and now you can move on to question number 7. Question number 7. Let's see here. Determine the exact value of tan pi over 8. And show all your work and simplify as much as possible. Okay, so as with a lot of these questions, the tricky part is determining where do you start. Okay, now pi over 8 is not an angle that's found in our special triangles, so using the special triangles directly is not an option here. If you try to do it on your calculator, you're going to end up with something that's not exact. So how do we do it? Well, I recommend at first, if you don't like the angle, try doubling it and see if you like that, because we have these double angle formulas that we can use if necessary. Pi over 8 is not very nice to work with, but if we double that, we get 2 pi over 8. Now 2 pi over 8 reduces to pi over 4, which, oh yes, we do like pi over 4. It's in the special triangle and we can work with it very easily. Now, since 2 times pi over 8 gives us an angle that we like, that's the hint to use the double angle formula. The question now becomes, which double angle formula are we going to use? You have a lot of them to choose from. However, since our question involves tan, when we look at our double angle formulas, we'll choose the one that involves tan. And there's only one of them, which makes the choice easy. Tan 2x equals 2 tan x over 1 minus tan squared x. Okay. So there is that double angle formula. What we'll do is, instead of x's, we'll use pi over 8. Okay, that's the angle we're interested in. And if we substitute in pi over 8 for every x, this is what we get. Now you might say, well, why would we want to do that? A couple reasons. One, on the left-hand side, you get 2 times pi over 8. Okay, it used to be x, now it's pi over 8. 2 times pi over 8 we know works out to pi over 4, which is great. We can take the tan of pi over 4. The right-hand side, it doesn't look as simple, but the good news is that it only has tan of pi over 8 in it, which is what we're trying to find. So you'd want to see it somewhere. All right, so we've made a good choice. Let's continue here. We said that 2 times pi over 8 is pi over 4. I just left the right side untouched for now. The tan of pi over 4, from a special triangle here, we see that there's pi over 4. Tan is opposite over adjacent. So we get 1 over 1, which is 1. We can rewrite tan pi over 4 as 1. Again, didn't do anything to the right-hand side here. So now the whole point becomes to try to solve this thing so it says tan of pi over 8 equals. After all, that's what we're trying to find if we look at the original question. So how do we do it? Well, we got some fraction action happening here. We got to get rid of that right away. Easiest way to do that is to multiply through the whole equation by 1 minus tan squared pi over 8. Some people like to call this, what we're about to do, cross multiplication. It's fine if that's the way you like to look at it. But when we multiply through by 1 minus tan squared pi over 8, we get no more fraction here. Instead, we get this, okay? And this came from just doing 1 times 1 minus tan squared pi over 8. Now, looking at this, we see that right away it's quadratic. It's a quadratic equation, a quadratic trig equation. And we think back to how we used to solve quadratics back in the day. And the best way to do this is to get everything on one side. Since tan squared pi over 8 is negative on the left-hand side, I'm going to choose to put everything on the right-hand side. So a little bit of rearranging gives us this, okay? Added the tan squared, subtracted the 1. We're left with this. So it is a quadratic trig equation, and ideally it would factor, okay? We can think of this equation as being something of this form, right? Something squared plus 2 something minus 1. There it is, something squared plus 2 something minus 1. Unfortunately, it doesn't factor though, but we can still solve it. If we were to solve this equation here where it doesn't factor, we could use the quadratic formula, okay? Now, we got to watch out. If we were to solve this using the quadratic formula, we'd be finding the value of x. In this expression, though, if we use the quadratic formula, we're not finding the value of x. We're finding the value of the thing that's in place of x, which is tan pi over 8. So when we use our quadratic formula, we're actually finding the value of tan pi over 8. And there's your formula there. It's negative b plus or minus root b squared minus 4ac all over 2a. If we simplify this a bit, evaluate it, we get root 8. Root 8 can be written as root 4 times root 2, which simplifies to 2 root 2. There it is. And we can divide 2 into both pieces of our numerator, giving us this. But you can't stop there. You got to check it, okay? Because something bad can happen here. You might be thinking, oh, great, I got it, the tan of pi over 8. It's just negative 1 plus or minus root 2. I'm done. Actually, no, you're not, cousin. We got to back up and say, are these both reasonable answers? And the truth is, one of them is not. Here's why. Pi over 8 is a pretty small angle. Okay, it's smaller than pi over 2. If we were to draw the terminal arm for this angle here, it would end up in quadrant number 1. Now, we know that in quadrant 1, all the trig ratios are positive. So tan should work out to a positive value in quadrant 1. But if we do negative 1 minus root 2, there's no way that's going to be positive. So we can't use the minus sign here. It leads to a negative answer, and tan of something in quadrant 1 should be positive. So we got to get rid of the negative option. Now, the positive option is fine because negative 1 plus root 2 is positive, as it should be in quadrant 1 for tan. Okay. For good form, we'll just go back up here and just cross off these negatives as well, because they technically shouldn't be there, should they? All right. Now, just to make it look a little bit prettier, instead of writing negative 1 plus root 2, we'll write it as root 2 minus 1. And that, folks, is the exact value of tan pi over 8. Pretty nice, eh? Okay, let's move on to question number 8. What do we need to do for question number 8? Solve, it's a trig equation. The cosecant of theta is 2.7451. So we have to find theta. And we're told that theta can be any value between negative 720 degrees and positive 720 degrees. Okay, as soon as you see this, folks, get that calculator in degree mode. Put your mind in degree mode too. Okay, we got to start doing everything in degrees. And we're going to round to the nearest tenth of a degree. Okay, cosecant. Cosecant's not the nicest ratio to work with. We know, though, that it's related to sine. So we might want to change it to something in terms of sine right away so that it looks like something we're used to working with. So if cosecant is 2.7451, then sine should be the reciprocal of this. In other words, sine theta should be 1 over 2.7451. Now, to get theta, the actual angle theta, you could try to go to your special triangle, but I don't think you're going to be too pleased with the results. 1 and 2.7451 are not side lengths in the special triangle. Fear not, though. We can still get the angle by inverse sining this value here, okay? And don't forget, when you take the inverse sine of this, what your calculator is telling you is the smallest value of theta such that the sine of theta equals this. As far as we're concerned, that's your RAA, related acute angle. So we take the inverse sine of this in degree mode, very important, and we get this, okay? I've carried some extra decimal places along here. In the end, we're just going to round it to the nearest tenth. What else do we have to consider? Well, we know that sine is positive. If we look back up at here, sine works out to something positive, which means we must be working with quadrants 1 and 2. And then, as usual, we just go and draw some pictures. Quadrant 1, related acute angle of 21.364. We need the angle in standard position, so it actually is 21.364. We can round this at this point, nearest tenth, 21.4. But that's not it, because the domain up here says we're allowed to go right down to negative 720 and all the way up to positive 720. So if we want, we can start adding multiples of 360 or subtracting multiples of 360 to our value here, as long as we stay within this domain. Okay, so 21.4, add another rotation gives us the same arm. So add 360 and we get 381.4. So far, so good. Can we add another 360 to this? No, we couldn't add another 360 because adding another 360 would put us past 720. So what's this all about? This is us subtracting 360 from 21.4. Because don't forget, we're allowed to go down to negative 720. Can we subtract another 360 from this? Yes, we can. Negative 698.6 is still within this domain. Obviously, we're not going to be able to subtract another 360, though. So that's quadrant 1. Let's look at quadrant 2. Terminal arm, quadrant 2, related acute angles 21.364. We need the angle in standard position, so we can do 180 degrees, take away 21.364, which gives us about 158.6 if we round it. But don't forget, we can go anywhere from negative 720 up to 720. So let's add 360 to this, get another possible answer. Can we add another 360 to this? No way. It's going to put us past 720. But we could go back and start subtracting 360s. Okay, so if we're here and we subtract 360, that'll give us negative 201.4, another possible answer. And another 360 off of that is 561.4 as another answer. Could we subtract 360 from this? Nope, because that would put us below negative 720. So look at that, 8 answers. So be a good person and put them in order. And there they are. 8 answers for theta. One more question to go here. Number 9. Okay, here it is, the last question. Question number 9. Using other identities, develop the tangent subtraction formula. And there's the tangent subtraction formula there that we're going to develop. Okay, well, the nice thing about this question is it didn't tell you which other identities you have to use. You can use any identities you want to prove or develop this tangent subtraction formula. So when you look at your trig toolbox, any of these are all up for grabs. You can use whichever ones you like. My recommendation would be use the tan addition formula because it's so close to the tan subtraction formula, and it's really easy to get from a tan addition into a tan subtraction. Okay, you could go back and use sine and cos addition and subtraction formulas if you want, but you don't need to because the question didn't say go back to that. So what we're going to do is we're going to make use of the tan addition formula to help us develop this formula. All right, here it goes. Tan x minus y is what we're trying to develop a formula for. So how do we do it? Well, if we're going to use the tan addition formula, the trick is to write tan x minus y. We want to write x minus y itself as an addition. Okay, we still want it to be x minus y, but we want it to look like an addition. And the way you do that is you write it as x plus negative y. These are the exact same thing, but this one looks like an addition. Why would we want it to look like an addition? Because now we can go use this other identity to help us. So this is where it gets a little bit weird, but in this case, if it was tan x plus y, we'd get this. So if it's tan x plus negative y, we'll get something that looks like this, but everywhere there's a y, we're going to replace that y with negative y. Okay? So we're pretty much taking this identity, this formula, but instead of y, we're going to use negative y. So here's what it looks like. Okay, there it is, tan x, tan negative y instead of y, 1 minus tan x, tan negative y, because we're using negative y. Now, we're almost there, actually. This is just about it. The only thing is tan negative y can be simplified, so we need to simplify that, okay? And we need to end up looking like this. So how do we do it? Well, if we look back at some of these little identities that we were working with earlier, one of them said that tan of a negative angle is the same as negative tan of the positive angle. In other words, tan negative x equals negative tan x. Okay, now we can talk about why that's true, where it comes from. It has to do with related acute angles and which quadrant it falls in. You can also look at it from the point of view of the tan graph, right? And essentially what this is saying is that tan is an odd function. In other words, if you sub in the negative angle, you'll get the same result as the positive angle with the opposite sign. Okay, I'd recommend that everything on this sheet you do remember for the test to just make it a little easier and quicker for you. Okay, so these are good to know. The only one that's kind of the exception is cos negative x. That works out to cos x. This is the one we're interested in. Tan of negative x is negative tan x. Therefore, tan of negative y can be written as tan y, but negative. Take a look at this. It's the same as tan y, but negative. Tan negative y is the same as tan y, but negative. Last but not least here, we've got a negative tan x times a negative tan y, so we can write that as a positive tan x tan y, which is exactly what we wanted. And you are done. Therefore, tan x minus y is tan x minus tan y over 1 plus tan x tan y. And that is it.